And my co-speaker is Shiyan. He's the founding member of the Onehouse and also the PMC of Apache Hudi. So for last whole year, we almost meet every week to discuss some technical details. So we want to share some learnings and the practices during the journey. This is today's agenda. So I will talk about a little bit about the background, the motivation of streaming ingestion at Uber. And then I will talk about the Cloud Lake ingestion and what's the methodology and the ecosystem. And the third part is some practices and the key learnings from the journey. Hopefully it can be useful for everyone here. Then Shiyan will deep dive into the Hudi Flink integration or also some roadmaps for advanced features. Cool. Let's quickly take a look at the Uber business. As everyone knows, that Uber has three major business units: mobility, delivery, and also Uber Freight. All those three categories of business relies on real-time data from user behavior and also the market data. So that's why actually Apache Flink is widely used in the company. We have more than 5,000 pipelines in production to support different products and use cases. For example, streaming analytics and feature engineering and the push notification. And in recent years, we find, okay, Flink can do more job in the Cloud Lake area. So we can accelerate those like data processing from data ingestion to ETL to make the Cloud Lake even better for our business users. So we talk about Cloud Lake. What is Cloud Lake? So back to almost 10 years ago, at that moment, Uber's business grew very fast. We built our own on-prem HDF cluster as a storage layer, and the whole data warehouse is on top of it. Starting from 4 years ago, we're starting to migrate our system into a hybrid cloud mode. Our real-time data, including microservices and also Flink, Kafka, Pinode, moving to the OCI. And our batch data side, mainly the data lake side, moving to the GCP. So those data is actually ingested into the GCS in this model. Currently, our scale in our Cloud Lake is 500 petabytes of data in Cloud Lake in one region. And we currently have more than 25K data set, raw data set in the Cloud Lake. Every day we ingest 600 terabytes of data. So before the streaming ingestion, the freshness SLA was like 3 hours to 24 hours based on tiers. You can imagine that high tier pipeline data set have like better freshness, but low tier we cannot guarantee too much. The actual observed freshness is less than 1 hour for P50, less than 2 hours for P90. So in this architecture, you can imagine that all the data stored as a Hudi table format with Parquet file format. On top of it, we have a Zuno compute resource for our Spark job and the Presto clusters. From the user perspective, they use our query builder, query runner to run those interactive queries to get data. And also we have provided a bunch of platform support UIs for users to understand the current status of the cluster and the query execution time and also data format, this kind of thing. And we're also involving our Cloud Lake by bringing the new AI initiatives. We currently have the Query GPT in production to support the analytics data analysis. And also we have some plan next year for the conversational BI to further improve our city operator to use the data for their daily operation in the city market. So why do we want to move those like so big guy into our streaming ingestion like new model? Everything is because of the business needs, mainly the real-time machine learning. I think in the morning keynote, we talk about data flowware, right? So basically we want to make sure that the end user features that needs real-time machine learning to do inference. And that model can be refreshed faster so that any user activities, model features can be ingested to the Cloud Lake faster, and with ETLs improvements, end-to-end freshness can be improved. So our incremental learning in the machine learning side can improve from daily run to even hourly run, so that any user activities, for example, someone take a ride or order Uber Eats in the morning, actually in the end, the model can capture signal and use that for our actually dinner ordering or even the lunch ordering. That's the major motivation behind the initiative to move into the streaming ingestion. So with this motivation, we set up goal as a project there. First, we want to achieve like a P90, less than 15 minutes append-only, like freshness for append-only data sets. We do see some complexity of the absurd data set. So we set the P90 to less than 1 hour data freshness. During this project, we definitely want to modernize the stack, reduce our operation overhead, and also reduce the cost. Because by using existing batch ingestion, we have dedicated Kafka cluster to make sure those like a batch read doesn't impact other high critical Kafka consumers. So if we move to Flink model, right, so we could actually reduce this additional dedicated Kafka ingestion cluster to reduce overall ecosystem cost. So with this background, let's take a look how the ingestion works end-to-end at Uber. So as you know, that we leverage Apache Hudi, which was originally from Uber. Like 10 years ago, we actually invented the Hudi in the Uber to resolve absurd use cases. We have a very large sharded MySQL database to store trips events. So the trip like last of like a long time will be like several hours. During that time, lots of columns will be updated. How to ingest this data into the data lake at that time, HDFS is a very challenging problem. With Hudi, actually, it supports absurds. It also provide different model, merge on read and copy on write to different use cases, and also it support incremental reads. So that no matter Spark or actually Presto, they can continuously read data with the last commit to Hudi commits, and also provides snap isolation. So on top of Hudi, we leverage Spark to do the end-to-end batch ingestion. We periodically run the job by using the Piper scheduler. It's an internal in-house solution similar as Airflow. Those Spark job read from Kafka convert data to Parquet and write to HDFS or GCS. So ingestion as a platform, they also provide lots of advanced features. For example, data quality monitoring, and also within Spark job, we have the inline compaction and also data archive. It actually improves data quality for the query engines. This is before the streaming ingestion work, how it works end-to-end. In this streaming ingestion project, we basically build a new ecosystem on top of our Flink platform to provide a scalable solution to allow Flink ingestion job read from Kafka and write to Hudi. And because we want to keep the Flink job as simple as possible, we don't want to do any inline like data clustering or compaction. So we move out these like table services from Spark job inline. So we have async table service period run to clustering the data and compaction the data. With these improvements, we in the platform we have built several major core functionality. For example, first one is that we enable the auto scaling in our platform to make sure the onboarding is easier. And in terms of operation, our on-call doesn't need to take care of the like spike traffics, the Kafka lags too often. And also we have the disaster recovery strategy. I will deep dive a little bit later for handling like a scalable failure over in the disaster situations. Yeah, those are like some background high-level architecture. During the projects, we do find some interesting things. We think about these problems in different angle. So I want to present in different way. Hope that it can be useful for everyone here. So first thing is like, so streaming ingestion is actually a trade-off, right? So you cannot easily find optimal configurations to do the work. Especially you need to handle 20K data set, starting from like small size topic or large topics. Before we deep dive that part, data quality is very important, right? We cannot tolerate any data loss. So when we do the Flink vanilla Flink Hudi application end-to-end run as a framework, we find some interesting things there. The first thing, let's take a look at how Flink Hudi works end-to-end. So Flink Task Manager internally has multiple operators, right? We definitely have the Kafka consumer. And our internal framework do some massage on the message. And then we have like a metrics monitoring to monitor data quality. In the end, there is a write function, the Hudi integrated operator. It will periodically write data to Parquet. And also during the checkpoint, actually it will flash out of the Parquet files. After this is done, actually those like write status will be sent to the write coordinator, which is actually get the buffer of the old task manager what the write status is. And the Flink Gen manager, once the old checkpoint finished, right, then it will notify the write coordinator to start the Hudi commit. The Hudi commit will have two dependencies. One is make sure each task manager writes successfully, and also the checkpoint completed, right? So we do see some issues with the write functions. Let's say we have some encryption issue, and cause some record have some errors. So the job can continue run, and somehow the error message will send the coordinator. At that moment, Flink commit, Flink checkpoint already finished, and our offset already moved forward, right? At that time, checkpoint, the Hudi commit failed, right? It's actually caused data loss. So we do some improvements to make sure this like Flink Task Manager can fail faster to prevent any data loss. And also, because we write to GCS, there's another interesting instance we find that during this GCS unavailable time within 1 or 2 hours, after that we find some data set have data loss also. What's the reason? Because after Flink checkpoint, when you write Hudi metadata into a file, right, it's still possible fail. In this case, to improve that, we actually add the Kafka offset into the Hudi commit. So basically, anytime if the job fails, it restart. It has the offset metadata to make sure there's no data loss. There are a bunch of advantage of this part. I will talk about a little bit later on the failure part. This is data quality. The second part, so we need to handle 20K data set in different data size. For the large data size, for large topics, right? So we see some interesting part is that somehow when we do vanilla Flink Hudi integration, we find the data partition size is 2 to 3 times of original data ingestion by Spark. What's the reason behind that? It is because the batch ingestion, we do additional global sort on this data on some common fields. So some related data will be compared together. The Parquet compression ratio is much better than the streaming ingestion. So it's not acceptable for those like downstreaming services, especially for HiveSync to copy data or Spark jobs. We do see some performance degree in terms of large-scale users. So to really improve that, we actually think about, actually we provide a buffer sort in the append write function. So with this sort supported, actually we can reduce the data size by improve the compression ratio. In the end, the partition size is only 1.1 to 1.3 times of original size. But after that, enable this for large topics ingestion, we still see some issues. We find that the CPU utilization goes down. What's the reason behind that? Because when we do the sort and the Parquet write, actually the buffer is blocked, and the back pressure is back compatible to the Kafka consumer. At that time, ingestion is like stopped. So to further improve it, actually we leverage the buffer sort, make the data fresh in the async way, and also make sure there's no data loss. It greatly improved the end-to-end throughput and the CPU utilization, but we add more memory usage for this use case. So it's a kind of trade-off. So you need to tune your jobs to actually handle different use cases and data sets. So in the end, we find that it is not an easy problem to resolve, especially when we have so many data sets, right? So we would like to say this is like an impossible triangle for you to achieve data freshness, storage cost, and cost efficiency at the same time. Anytime you can only achieve 2 of them, right? For batch ingestion, you can probably have very good storage compression ratio, and you have better query efficiency and the less table service work there on the data set after ingestion. But for streaming ingestion, you can definitely have better data freshness, compromise the storage cost. But in terms of query efficiency, you probably need a table service to kick in after 1 or 2 hours and then make the query more efficient in the end. So how can we find the optimal parameters for those different data sets is a question in our mind. So with this as a question, we jump into the Flink Autoscaling as a service internally. So I think if you use Flink very often, I think autoscaling was introduced into the Flink Kubernetes operator like 3 years ago in Apple. And also they have lots of advanced features for memory tuning there. So we bring this algorithm for our use case. It's very useful to determine the initial parallelism. So when we onboard new topics, right? So you have different schema and also traffic volumes. It's hard to determine the initial parallelism. If it's wrong setup, it will actually overuse the CPU and the resource there. Autoscaling plays very well role there to find the optimal initial parallelism. And autoscaling can also handle some spike traffics and also fail problems. So let's take a look at the basic algorithm, right? So how does the Flink runtime determine those like right parallelism for the job? So the key point here is, this is from the OSDI original paper, 2018 actually. Basically the key here is within Flink, each task, it will try to monitoring for each task what's end-to-end time used for waiting for input buffer, output buffer, and what's real time used for the calculation and the computation. So each task you can find what's the business ratio for that task as a key point. This is a parameter of the per task capacity. And we have the current observed last like 30 minutes of buffer, what's the input rate. And also user can specify targeted utilization, right? What kind of utilization you want to achieve. Based on the current input, you can find the baseline capacity. If your job fail and try to recover, you can also calculate some of the lag recovery capacity. This is actually in terms of number of message per second, right? End to end. So you divide this total capacity by the per task capacity. You technically can estimate what the parallelism should be for particular task can handle the workload without a lag, right? And if your job have multiple tasks in an execution graph, basically the job parallelism is the maximal parallelism of all the tasks. That's the basic algorithm. But we find that it cannot handle all of the use cases. Especially, it's hard for us to use this algorithm to find optimal configurations. So first, we enable the delayed scale down to prevent frequent scale down. This is a feature already exists in the Autoscaler, latest version Autoscaler. It's very useful for Uber because you can imagine that our traffic time is different. During noon, during evening, right? So the traffic is high because more people order food, more people take rides. But the other hours is not too much traffic. So it's a 24-hour daily patterns there. So delayed scale down 24 hours, we prevent unnecessary scale down and the rollback of the jobs. We enable that, but still we cannot handle some of the problems. This is the peak traffic. So during the peak traffic, we have the some special holiday seasons that has a Super Bowl, right? So the traffic is super high. It's the traffic can grow 3 times, 5 times the normal. In this case, Autoscaler only calculate last minute buffer data to do the local optimization of calculation. So at this moment, we need to rescale multiple times. Because Hudi commit has data write out. When it fails, it can recover, the rollback to clean up the packet files, uncommitted packet files. In this case, it will cause additional lags and latencies for end-to-end ingestion. So how do we handle it? We identify we can actually extend this algorithm by leverage external metrics, right? So currently, Autoscaler can only leverage the Flink runtime metrics. Whether we can have an external system for each Kafka topic, we have periodically checking what's the peak traffic every day. For last several years, we can add some like estimate for every day what's the peak traffic, and use that as a total capacity to estimate the parallelism. So in this case, every day we only need to scale up once for the daily traffic to prevent unnecessary restarts. And then actually, we also want to say whether we can tune other parameters for the job. For example, the checkpoint interval, right? So the total data of size for each Hudi commit is controlled by the Flink checkpoints. If you have small checkpoint interval, data fraction is better, but less data to ingest it. So the file size will be small, which is not good for the query efficiency. And in this case, if we can adjust this like auto-scaling algorithm with different dimensions, then we can actually propose a better auto-scaling algorithm for our use case for different data size of the topic. So this idea was proposed in the Flip 543. We are internally exploring these ideas. Hopefully we can share these improvements in the upstream, the more people can use that in the future. With this performance optimization, we also have a bunch of work to improve our deployment. You can imagine in the end, currently we already onboard more than 100 jobs in production. So we target 20K, right? So at Uber, we build a Flink service. You can imagine our user can write Flink Java code, operate Flink job as a service, microservice. And these jobs can be organized in different environments. And we have CI/CD enabled, automatically roll out those changes from dev staging to production. Our end users also use their data set tiering to organize these environments. So we can guarantee the safe deployment rollout for those changes, especially like a Flink version upgrade, like a Packet version changes. All those things can be guided by the safe deployment. And also we have metrics monitoring to make sure there's no performance degrade, no issues. If there's any issue detected, we will roll back. So this is the way we reduce the development and the maintenance effort of this of our users. Actually, our colleague will have another session after this talk. Please go to that section to understand more about these advanced features. The last one I want to talk about is the disaster recovery. Actually, this is a very important and interesting topic there. So as I mentioned, we moved to the cloud, but is cloud 100% reliable? It's not actually really not, right? So we do see some issues. When we onboard OCI and checkpoint to OCI, we do see some object store outages. Our Flink job down several hours. Even for last year, we also hit the GCP outage because of networking issue, and also whole zone goes down. It takes almost more than 8 hours to recover, right? So especially for those critical data set, ingestion data set, we need to really prepare for the disaster recovery. What's our solution? So we have the all-active setup. So basically, we have only primary region, which is region A, to the real-time ingestion. As you can see, day one, day two, as you can see, this is kind of Hudi partition by day. And the C1, C2 is actually Hudi commit. For the Flink job running in the primary region, it periodically committed offset to the Hudi commit. But as you know, that Flink cannot access state of other operator, right? How do we do that? We build actually a Flink checkpoint service, which is the cloud agnostic. It will fetch the metadata from the checkpoint and find out what's the offset, and then checkpoint happens. And use that offset to commit to the Hudi metadata. In this way, our Hive sync will replicate data from the primary region to second region. And then you can imagine that the Hive sync takes time. So there's some additional commit lag. If you want to understand more about the Hive sync, there's our Eng blog recently published. When the one region A goes down, right? So basically, there's no compute here. So we need to start failover jobs in the second region. And the second region will pick up the latest committed commit offset into the copy the data from the primary region and find out, okay, where is the offset for our secondary region Kafka offset. This is also the feature provided by Kafka team to make sure there's no data loss to continue to run. So in this case, we can guarantee single job. When disaster happens, we can continue to ingest data and also guarantee data completeness. But this is for one job. How do we handle so many jobs? 20K jobs. So we actually we need to coordinate those like failover from ingestion to ETL and to end-to-end data consumers from Spark job, Presto jobs. So we have a workflow coordinations to leverage the data lineage to determine what's the failure zone and understand what are data set or pipeline to be failover. And then we have the workflow to coordinate that to make it happen end-to-end. So in the end, actually want to summarize, we extend our Flink platform to have some advanced functionalities. So first, we improve the runtime efficiency by introduce some advanced features to improve runtime ingestion efficiency. And we bring our safe deployment model into our ingestion workload. And we leverage the autoscaling to reduce the cost and also operation overhead. In the end, we provide the disaster recovery capability to make sure any ingestion pipeline run within our system can easily handle a disaster by failure to second region. So then our next step is we will continuously improve our scalability and the failure support. We will implement onboard more data set and continue to contribute to our Flink Autoscaler customized algorithms for ingestion workload. We will also explore together with the Hudi community about the Flink Hudi upsert data set and also evaluate the Flink streaming ETL in Cloud Lake. Let me pass the talk to Shiyan for the next part. Thank you.
All right. Thank you, Peter. Flink is really a powerful streaming execution engine. Hudi also implemented many architectural designs cater for streaming use cases. By combining the power of Flink and Hudi, you can effectively build a high-performance streaming lakehouse at large scale. So first, I would like to provide a 10,000-foot view of how Hudi is identified as a comprehensive lakehouse platform. A lakehouse starts by storing a vast amount of data on the storage layer. Think about Amazon S3, Azure Blob Storage, and Google Cloud Storage, or HDFS, with data stored in file formats like Parquet or ORC. At its core, Hudi defines a table format. Table format describes the table layout. It determines what data needs to be stored and maintained so that it can properly describe the raw data files on the table-based path. And it also defines how the metadata is structured. This is the key to ensure the raw data can be efficiently manipulated by all reads and writes operations. Based on this table format, Hudi implements the storage engine. On top of that, it's a transactional layer, it's transactional database layer that understands the Hudi table format and delivers essential lakehouse capabilities such as indexing, table services, and concurrency control. So when it comes to data ingestion, Hudi can seamlessly integrate with various execution engines such as Flink or Spark. These engines plug into the various data sources such as operational databases like Postgres or event stream platforms like Kafka or Pulsar. So once read data from those sources, this execution engine, because they are integrated with the storage engine defined by Hudi, provided by Hudi, they are able to write those data as Hudi tables, so which forms your lakehouse based on Hudi tables. To make the data universally accessible, Hudi also implements a catalog sync mechanism. This catalog sync will be able to register Hudi tables with various data catalogs, which enables a wide range of query engines to be able to query the Lakehouse tables in Hudi. So to manage the large amount of tables, Hudi also provides platform components to effectively manage thousands of tables often found in large data platforms. So with this high-level structure overview, let's discuss Flink and Hudi integration features. First, let me introduce Flink's dynamic table concept. In Flink, a changelog string can be converted to a dynamic table. It's a logical concept. It reflects all the changes for each row originated from the stream in real time. As you can see from the upper left side, it is a stream of user click events. The corresponding dynamic table shows the same data. And in addition, it allows SQL queries to perform reads and do transformations and aggregations on top of that dynamic table. So such queries are called continuous query, which never terminates. Flink's processing pipeline can consume one dynamic table and perform continuous queries, do computations, and produce another dynamic table as a result, which can be converted back to a stream. So this can achieve a pipeline training effect. Flink uses its state backend to store any required information for such intermediate state that is required for some continuous query. For example, if you do accounting, the counts needs to keep accumulating, keep some counts in the state backend so that it keeps accumulate new counts based on some record key. However, Flink state backend isn't optimized for large-scale analytics. This is where Hudi can be used as a materialization layer. So leveraging Flink's dynamic table, Hudi introduces changelog mode, which is designed specifically for working with this scenario. Changelog mode in Hudi is a straightforward implementation where we preserve all the changes exactly as they come in. In Flink, we have row kind column defined in dynamic table. The row kind column represents different operation types like insert for new records, update before, update after for updated records, and delete for deleted records. So on Hudi side, we introduced a new metadata column that stores alongside with each record in the Hudi table. We call it Hudi operation. So the column is meant to it's meant to keep track of the row kind from the Flink dynamic table. So when writing to Hudi, when you choose MOR table type, Hudi stores these changes in log files. And Hudi uses compassion to merge the log file with the base file to produce a new version. Therefore, if any reader that consumes these changes from MOR table, these changes can be read as streaming changelog. So the Hudi table actually acts as a source. So one limitation about this approach is the upstream source for Flink, it has to support deriving changelog. For example, a common example of such stream of changes is one produced by Debezium CDC, which pulls changes logs from operational databases. Zooming out to a higher level, looking at the data architecture, Flink usually consumes upstream messaging data sources like Pulsar or Kafka and do continuous processing. So leveraging Hudi's changelog mode, a changelog string can sync into Hudi table. Hudi table serves both as a sink and a source for streaming. And it can generate new changelog streams for further processing, thanks to the incremental semantics defined by Hudi. So these dual functionalities of being both a sink and source can enable operations like SQL joins and aggregations, allowing us to create bronze, silver, and gold layers of tables for a wide range of analytical needs. This architecture is also known as medallion architecture. By combining Flink and Hudi, we've created an incremental streaming ETL pipeline that addresses the limitation of traditional batch processing. This approach reduces latency and opens up new possibilities for real-time data analytics. Hudi also has generic streaming-first designs to address challenges raised during streaming writes. Let me give a brief overview of 5 design highlights for 5 challenges when you do streaming writes. First, high-frequency updates. Hudi leverages MOR table type to absorb changes quickly into log files, which minimize the write amplification. For large volume of mutable workloads, Hudi implement record-level indexing on the writer side so that it can efficiently locate records and improve the overall write latency. During streaming writes, small file proliferate. So Hudi uses auto-file sizing and async compression and clustering to optimize file sizes without interfering with the ongoing write operation. With optimistic concurrency control, or OCC, conflicts happens quite frequently with streaming write scenario. Hudi implements non-blocking concurrency control, or NBCC, to avoid costly retries. Finally, when doing a lot of streaming writes, you will accumulate a long history of commits to a Hudi table, which adds a lot of read and write overhead. Hudi implements log structure merge tree to optimize the storage and loading of such long history of commits. So I have another talk later to discuss all these points in much greater detail. Feel free to join me at 4:30 in the same room. The Hudi community keeps improving Hudi and Flink integration. So to highlight some roadmap items, the integration with new Flink source API introduced in Flink 27 will improve auto-scaling, back pressure handling, and regional failover. Bucket index is a high-performance hash-based writer index used by Flink Hudi writers. By implementing the dynamic scaling feature for bucket index, the write performance will be addressed. There are a lot of write performance challenge in dynamic changing streaming workloads, so those will be addressed effectively. The Hudi community welcomes all sorts of contributions and new proposals, including improving the integration with Flink. Thank you very much. And